Meanwhile, Sias can once again put a reminder in group asking those who have not joined to join. Right. So, good afternoon, everyone. Welcome to yet another online tutorial on Advanced Communication Lab. So, we have completed our cycle 1, that is discrete component implementation of digital communication systems, right? So, and in part B, we have 4 Matlab experiments, and about the details of those 4 experiments we have seen in previous video, right? So in this video, we'll straight away start with DPSK modulation and demodulation. So what we'll do in this session is we will be simulating the mathematical model of differential phase shift keying and its non-coherent detection using Matlab. Matlab online. I'll be using Matlab online. I believe all of you have access to Matlab online, and I request you all to try it simultaneously along with me, so that you can finish it up. As we finish this session, you might have executed this sorry simulation of DPSK. Next week, again, you can do the same. So initially, before we start with the simulation, we'll just discuss what exactly is the mathematical model of differential phase shift keying, right? So differential phase shift keying, right? You can see it as actually what a variant of DPSK, right? It is a variant of binary phase shift keying, right? Wherein it involves differential encoding, right? Differential encoding plus phase shift keying, right? Differential encoding plus phase shift keying. So in BPSK, what we did is, if it is a 1, we'll be transmitting in phase, and if it is a 0, we'll be transmitting also out of phase signals. You have implemented it in using discrete components in multi-sim, right? Whereas in DPSK, right, unlike this BPSK, we have a differential encoding part, right? Differential encoding part, which actually helps this BPSK to perform better when we have a noisy environment, and also we can it actually what facilitates the non-coherent detection, right? So we have discussed those things. So maybe I'll start by discussing what exactly is the mathematical model, and what is it, how to implement that, right? So what we have is, we have this data sequence or information sequence, right? We have data sequence that will be 1s and 0s, right? So we can consider some arbitrary bit sequence. Say I'll consider 1 0 1 1, for instance, right? So we have this bit sequence, right? So in differential encoding, what happens is, we will before even modulate these data sequences, differentially encoded. So how differentially encoded? So we have a block, right? Differential encoding block. It will perform XNOR operation, right? It will provide a 1-bit delay. So a current bit will be XNORed. So this operation is nothing but what? XNOR, right? So current bit will be XNORed with the previous bit. So this is the differential encoding part. So this is what we have to solve. We have bit sequences. So initially it should be differentially encoded. So that differential encoding is nothing but what? Current bit XNORed with previous bit, right? So that's what it should happen initially, right? Then so what actually is, can anyone help me out with the truth table of XNOR? So if it is 0 0 0 1 1 0 1 1, right? If it is XNOR, right? 0 XNOR 0 will be 1, and 0 XNOR 1 and 1 XNOR 0 will be 0, and 1 XNOR 1 will be again 1. So this is the XNOR truth table. So accordingly, right, this is actually what differential encoding. And initially, right? Initially, for the first bit, there is no any previous bit. So in our case, what we will do is we'll assume the previous bit to be equal to 1. Right? We'll assume the previous bit to be equal to 1 while performing differential encoding. The initial bit we'll assume to be equal to 1. You can even assume it to be equal to 0. It's up to you. But here we'll assume it to be equal to 1. Right? So then once differential encoding is done, what we'll get is, again, we'll have actually what differential encoded signal. It will be ones and zeros only, right? So we have to convert it into what? Polar non-return to zero format, right? Polar non-return to zero format, right? What actually is this polar non-return to zero? So what it does is, if it is a 1, right, it will be converted to plus root EB, where EB is the energy per bit, right? And if it is 0, it has to be converted to minus root EB, right? For convenience, what we will do is we'll assume this EB to be equal to 1 here. So, but you can always assume this EB to be equal to any value, not a problem, right? So this polar non-return to 0, what it does is it converts ones and zeros to plus 1 and minus 1 respectively, right? So it is, this signal is, this data is converted to or line coded into a polar non-return to 0 format, right? Then further, what will happen is, this is actually what DPSK modulation. In DPSK modulation, it is nothing. We can straight away multiply this polar non-return to 0 encoded bit sequences with our carrier or the basis function, right? The basis function or carrier is root 2 by t cos 2 pi fct, right? Carrier is root 2 by t cos 2 pi fct. So now the, why this root 2 by t? This root 2 by t implies it has unit energy, right? Unit energy, right? Any signal of the form, if the amplitude of a signal is root 2 EB by t, right, you can say energy of that RF pulse will be EB, right? So we need we are multiplying this plus root EB or minus root EB with root 2 by t cos 2 pi fct, so that the resultant signal will be plus or minus root 2 EB by TB or root 2 EB by t cos 2 pi fct. This will be the modulated signal, right? The modulated signal will be plus or minus root 2 EB by TB cos 2 pi fct, right? So this is just like our binary phase shift keying, right? Either a symbol 1 will be represented using a plus positive RF pulse, and positive in the sense in phase RF pulse, and symbol 0 will be represented using a out of phase RF pulse. So this is actually what the modulated signal, you can call it actually S of t, right? So this is a modulation. But one question is, what should be the carrier frequency? What should be the minimum carrier frequency, right? So in practice, we don't have to bother about the carrier frequency. Why? Because this mainly DPSK or in general PSK, it is used in, for instance, wireless LAN, right? IEEE 802.11b, right, which was a 1999 release, right? So for that service, there is a specific frequency of carrier that is required, right? So in such cases, you have to use that frequency itself, right? And it's even used in actually what Bluetooth version 2, Zigbee, right? And even in RFIDs, right? Generally, phase shift keying, right? So for differential phase shift keying, it's actually what a variant of binary phase shift keying, right? So it's also used in fast wireless LANs in association in along with actually what OFDM. So those are some of the applications. So in those applications, the carrier frequency which are to be used is fixed, right? But in our case, right, what we will do is the carrier frequency, we will take it to be numerically equal to the bit rate, right? I want you to like appreciate this concept. We'll be taking carrier frequencies equal to bit rate. The reason is, right, if I want to represent a 1 or 0, so for a complete bit duration, minimum 1 cycle should be there. Minimum 1 cycle of a carrier should be there within a bit duration, right? So it will be satisfied only when FC is at least equal to what? Bit rate numerically, right? So at this point, if you have any doubt, please unmute yourself and ask, right? If you type it in chat window, I may not be able to see, right? Apart from that, A section and B section students are in different rooms, right? So if you have any doubt, please feel free to unmute yourself and ask, right? So this is differential phase shift keying. So it is actually what initially differential encoding followed by phase shift keying. So maybe first we'll do the modulation part, then we'll come back and do the demodulation part, right? So in modulation part, what are the inputs to your program? Your inputs to the program should be, you should provide information sequence, right? Information sequence or datas, right? Ones and zeros. And you should also tell what is the data rate, right? You should also tell what is the data rate, right? Given information sequence and data rate, right? We will generate a DPSK signal assuming carrier frequency to be equal to data rate. That is what we are going to do now. So is this clear? Right. If it is clear, we'll try and simulate this part, then we'll come back, right? Otherwise, do you want me to discuss the demodulation part also and simulate it together? I think initially we will simulate the modulation part, then we'll come back to demodulation part. But before I move ahead with simulation, if you have any doubt, please feel free to ask. Right? Any doubt? Are you clear what we are going to do? So it's not like a discrete component implementation or real time implementation. We are going to simulate the mathematical model, right? So mathematical model is nothing but what? Initially differential encoding, then the differential encoded signal should be converted into polar non-return to zero form. Then straight away you have to multiply the polar non-return to zero encoded signal with our root 2 by t cos 2 pi fct. That's what we are going to do, right? So now, okay, I'll be using Matlab online live scripting to demonstrate this, right? So if you can do it along with me, please do that. Otherwise, please pay attention here, take down some notes, right? Try it out later. Right, so I have to save time, right? If I sit and type now, I won't be able to finish it. So I've already typed in the code here, right? In Matlab live, Matlab online live script, right? So are you able to see this? Is it visible, or should I zoom it in a bit? Can anyone give me a feedback? Yeah, okay.
Can you zoom, sir?
Zoom, okay, fine. 1 second. Right, how about this? Is this fine?
Yes, it's clear, sir.
Yeah, okay, fine. Yeah, so now initially I told input to our program should be the bit sequence. So we'll be considering 10 bits, right? 10 bits, zeros and ones, and we'll be assuming the bit rate to be equal to 1 gigabits per second, right? 10 power 6. You can assume any value, right? So in this case, we are assuming the bit sequence to be this, right? Or else you can generate actually some random bit sequences. You can use Bernoulli bit sequence generator, which is available in Matlab, or any other method you can use, right? But in this case, we'll be assuming the bit sequence to be equal to 0, 1, 0, 0, and so on. And bit rate, I've defined it to be equal to what? 10 power 6. It is in bits per second, right? And frequency, carrier frequency, I've given a variable name to be equal to f, and I have assumed it to be equal to br. So this is the minimum carrier frequency, as I told just now. For you to modulate, at least one complete cycle is required per bit duration, right? So that's why I have assumed the carrier frequency to be numerically equal to bit rate, right? Then bit duration, t is 1 by bit rate. This is 1 bit duration, that is 1 by bit rate. And now I am defining a time vector for 1 bit duration. So later on, what we will do is we will generate the modulated signal for individual bit duration, and then we'll append it, or we'll concatenate them to get the final modulated signal. And before we move ahead, I would like to have a submission. This is not the only way to simulate a DPSK system, right? There can be many other ways, but this one is I'm trying to imitate the exact mathematical model, right? Same process I'm trying to implement, right? You can even use Simulink, but if you use Simulink, that becomes quite easy. Why? Because in Simulink you have ready-made blocks for say BPSK or DPSK or QPSK, right? Maybe further when you are trying to evaluate the error performance and all those aspects, you can use Simulink, right? But for this, we'll be using Matlab, right? So I think this first part is fine. So what I'll do is I'll just go to live editor. I'll write section by section. So initially we have defined all the inputs, and from that input, whatever we can actually derive, obtain, that also we have done. So I'll run an advance now, right? I've run an advance. So initially I've defined the, right? So, and now we have to plot this, right? So bit sequence, we have to plot. To plot that, I'm using stem, right? Stem actually gives a discrete plot, right? So I'm using stem. I'm not plotting it actually with respect to what exact time and all. If you have to plot like that, you can use actually say even stairs you can use. But when you use the function stairs, you will get some problem. But I think you are already familiar with these things. I don't have to spend much time, right? So I'll be using stem to plot this. So let's just, I'll just run an advance, right? So I have plotted it. This is the information to be transmitted: 0, 1, 0, 1, 1, 1, 0, 0, 1, 1. This is the information to be transmitted, right? So we have our information to be transmitted, right? Next, what we should do is we should differentially encode it, right? So we have to differentially encode it. So what I should do is I should take bit by bit, right? First bit is 0, right? I have to XNOR it with the previous bit. So initially we don't have any previous bit, so we'll assume the previous bit to be, initial previous bit to be equal to 1, right? So I'll be naming that previous bit as DK, right? So DK is our previous bit, right? I'll be naming DK to be our previous bit. And initially, and one more thing, after differential encoding, if our bit sequence has 11 bits initially, after differential encoding, of course, we'll have 11 bits, right? Initially, we had only 10 bits, but after differential encoding, we'll have 11 bits, right? So please do keep in mind this initial bit is required, which whatever be the assumption, right, that also should be modulated and transmitted. Otherwise, we won't be able to demodulate it at the receiver end. So if we have 10 bits in the original information sequence, after encoding, we will have 11 bit. The 11th bit is the one which we prefixed with the original bit sequence, right? So you can assume it to be either 1 or 0. It's not a problem, but that also should be modulated and transmitted. Then only you will be able to demodulate it reliably at the receiving end, right? So that's the case. So DK is the initial bit. We are assuming it, even though our initial bit is 0, the previous bit, we are assuming it to be 1, right? Then I'm giving the name coded, right? Coded will be the differential encoded output. So initially the coded sequence will be only DK, right? It will be a one-dimensional array or a raw matrix, raw vector, and initially it will be only DK. Then later on, what I'll do is I'll XNOR the current bit with previous bit, and I'll keep on appending it, right? That's what I'm trying to do. So I'm going to use a for loop, right? For I from 1 to length of BK. If you remember, this BK was our original bit sequence, right? We had 10 bits, right? So it was a 1 cross 10. So this for loop will iterate for say 10 times, right? So for I from 1 to length of BK, then you have to perform XNOR operation. So XNOR operation, that is, we have XOR in Matlab, right? We have XOR, right? If you negate it, right? If you put a tilde on left hand side of XOR, it will become XNOR, right? It's actually what XNOR is. not of XOR. That's it, right? So this is the syntax of XOR. XNOR of the 2 bits. The first bit initially it is DK and second bit is BK of I, right? So and we are saving it in a, a variable temp, right? You don't have to do it. You can write it in a single line also, right? But for you to break down and analyze, I have written it like this, right? So this temp is actually what current bit XOR with previous bit, right? Then what you should do, you should concatenate this temp with coded bit, or you should append these new values with the coded bit. So coded is equal to coded space temp. What is the meaning of this? What does this mean? So coded, right? So to this coded, I'm adding a new column, right? To this coded, I'm adding a new column. That is actually what temp, right? So then what we should do is now the previous bit, it will become temp, right? So this X node, whatever is X node, that will become this DK, the previous bit. So DK is equal to temp, right? So then, so we have differentially encoded it. Maybe I'll just run this section in advance, right? So now this is the differentially encoded signal, right? Differentially encoded signal, and we have to plot this, right? We should plot this differentially encoded signal for that, right? For that, right, you can see now, even though our bit sequence, original bit sequence had only 10 bits, now we have appended this initial assumption 1, or we have prefixed it, and these are the differential encoded things. So we have 11 bits in the differential encoded bit sequence. Now what we should do is we have to, right, we have differentially encoded it and we have displayed it. Further, what we'll do is we'll try and plot this, right? We'll try and plot this. For that, sorry, differential encoded bit sequence I have plotted, right? This part is actually what plotting of differential encoded bit sequence, right? I hope all of you are able to see this, right? We have plotted this. Okay, yeah, we have plotted this differential encoded bit sequence. I was running one section ahead, right? That's why I was getting confused. So this is we have plotted the differential encoded information sequence, right? Now next what we have to do, the differential encoded bit sequence is either 0 or 1. But if I have to perform a phase shift keying, especially binary phase shift keying, what I have to do is I have to convert the signal into a polar form, right? Convert the signal into a polar form. For instance, when you implemented a BPSK system, in discrete component, right, we wanted our input to be either plus or minus 1, right? So some were asking, what if I use a clock pulse, right? If you were using a clock pulse, it's either 0 or positive, right? So it cannot actually drive a p-type and n-type transistor, sorry, a NPN and PNP transistor, right? So maybe you can relate it to that, right? Or else mathematically, it's plus root 2 EB by T cos 2 pi FCT for 1 and minus root 2 EB by T cos 2 pi FCT for 0. That's what we are transmitting. So next what we have to do is we have to convert the coded bit sequence into polar non-return to 0. So for that I'm using a very simple logic, right? For that I'm using a very simple logic for this differential encoding. Just see here, right? If the bit sequence is 1 0 1 1, right? If I multiply this bit sequence with 2 and finally I subtract 1 from each. When I say multiply each element, and when I say subtract from each element, what I'll get, it will be 2 into 1 minus 1 will be 1. Wherever we have 1, that will be retained as 1. Wherever we have 0, it is 2 into 0, it is 0. 0 minus 1 will be minus 1, and 2 into 1 is 2. 2 minus 1 will be 1. 2 minus 1 will be 1. So if you do this, what it does is, wherever we have 1, it will be retained as 1. Wherever we have 0, it will be replaced with minus 1. So this is actually what one simple logic for converting unipolar non-return to 0 to polar non-return to 0. Right. So that's what we have. That's how we have done. Right. So yeah. So that's what we have done here. You can see here coded polar non-return to 0 is equal to 2 into coded minus 1. Right. Coded individual bits of the coded sequence is multiplied with 2, and from each individual element we are subtracting 1. Right. So that we will get coded PNRZ. Right. Then we have to do the modulation. So first step is, so this is actually what differential. Maybe I'll write as command. Right. It is unipolar to polar conversion. First step is unipolar to polar conversion. Then I told what we'll do is bit by bit we'll generate the modulated signal. Then we'll append it one after the other. That's what we are going to do. Right. So for that, again, we have already defined the time vector for 1 bit duration. So once again I have written here for you to what? Remember, T is equal to this capital T is 1 bit duration. This capital T is 1 bit duration. That is nothing but what? 1 microsecond. Why? Because our bit rate is 1 megabits per second. That is 10 power 6 bits per second. So 1 bit duration will be 1 by 10 power 6. That will be 1 microsecond. Right. So we are assuming say 100 samples. Right. So to define that, you don't have to do this. Right. You don't have to do this. Instead of this, you can. I'll just type it in command window. Right. Instead of this, you can use this command like linspace. Right. Start value, it can be 0. End value can be T, and number of samples. Number of samples, if you want 100 samples. Right. This also would be fine. Right. So instead of this. Right. So then you will get 100 samples between the starting and end point. So instead of that, what we have done here is we have taken T by 99 as the first sample of time. Right. Then T as last sample of time, and then we will be considering what samples at every T by 99 interval. Right. So these and all, it's up to you which is to use. But one thing which you have to keep in mind is if you have to plot a signal, right, the time axis and the signal should have same number of elements, right? So otherwise Matlab will show errors. So that's why you should, if you are following up, if you are using linspace, right, stick to that and make sure the number of samples in the signal as well as in the time vector both are same, right? So here I have used this, right, starting from T by 99 to T, we are considering 100 samples, right? So that's what I've done here, right? So now this is the time axis for 1 bit duration, right? Time axis for 1 bit duration. Now what we are going to do is for I from 1 to length of coded. Length of coded will be 11. So there are 11 bits. So we have to modulate all the 11 bits, right? For that, what we have to do is we have to simply multiply, right, this coded PNRZ of I, right? That will be either +1 or -1. In fact, it would have been plus root EB or minus root EB. For convenience, we have assumed that EB to be equal to 1, right? So we have to simply multiply this coded PNRZ with our message signal root2 by T cos 2 pi ft. Right, so that is the modulated signal for 1 bit duration. So what we should do is initially I have assumed this modulated to be a null vector, right? Initially the modulated signal vector, it was a null vector, it didn't have any element. So now what I'll do is after each iteration, the modulated signal corresponding to each signal will be appended to it. That's what is being done here, right? That's what is being done here, right? Modulated is equal to modulated with the term appended to it at the end, right? You can either give a space or you can even give a comma. Please don't give a semi, like if you give instead if you give a semicolon, it will go to new line, right? So you can either here you can either give a comma or a space, right? Both are same. But if you give a semicolon, it will go to new line. It will be added as new row. Now we are appending new columns to it, right? So this is modulation, right? And after modulation, right? So this is the modulated signal, right? This is the modulated signal. This is how we have plotted. Maybe I'll just undock this and show. Okay, I didn't run this. Okay, maybe I should run this, and after that I'll undock this and show. Right. So this is the DPSK modulated signal. I'll just undock the signal and show, and maybe we'll compare it with our encoded bit sequence. Right. I hope all of you are able to see this. Right. I hope all of you are able to see, and right, the encoded bit sequence was, what was the encoded bit sequence? Information bit transmitted. After that encoded bits, I'll just come to that encoded bit sequence. Right. So differential encoded bit sequence, you can see this is 1 0 0 1 1 1 1 0 1. Right. So wherever we have actually yeah, so initially it was 1. So for that we were transmitting a plus course, right? You can see this is 1 bit duration, right? This much is 1 bit duration, right? So initially it was a 1, so we are transmitting a plus course, right? Then what we have is 0 and 0. So for 0 we are transmitting minus course, right? 2 bits. Then again we have actually what, 1 1 1 1. So for that we'll be transmitting plus course, right? Then 0. So it's again actually what, same as DPSK. If it is 1, we'll be transmitting plus cos, and if it is 0, we'll be transmitting minus cosine, right? It is exactly the same, but what you have to keep in mind is we are using the differential encoded signal to modulate this high frequency carrier, right? So it actually what creates some difference, right? So this is the DPSK modulation, right? This is DPSK modulation. Now we have to see what is DPSK demodulation. So before that, if I may ask, any doubt is there? Right. If any doubt in what we have done so far, right? So now you may find it is easy, but for exam, you will have to do it all by yourself. Right? I'm not telling it's very difficult, right? But even then, students used to, right, find it difficult. A day before exam, they used to tell, sir, can we like not keep this particular experiment? We'll keep only 2 from Matlab, right? So that is because maybe if you are not paying attention now and you are trying to read everything a day before exam, definitely you are going to be in trouble, right? So I request, if possible, right, do it along with me, right? Or else I'll share the codes. You can try it out later, right? So in any doubt and till here, right? In modulation part, do we have any doubt? I think it's too simple for you people, right? You people are doing, right, much complicated things, and we are coming here with a simulation of BPSK signal or DPSK, right? So can I go ahead with demodulation? Can anyone? Shall we go ahead with demodulation? No doubts. Okay, Carlton has typed at least no doubts, right? Okay, I think we'll go ahead with demodulation. Yeah. So now for demodulation, initially I'll just tell what is the mathematical model of this demodulated signal, right? So now what we have is the modulated signal. So I'll call it S of t for convenience, right? This S of t, normally in BPSK, what used to happen is it used to be coherent demodulation, right? So S of t in coherent detection or coherent demodulation, what we used to have is we used to have a local oscillator producing. This is not the case of non-coherent detection. I'm just telling what normally happens in BPSK, coherent detection, right? Cos 2 pi FCT, right? So S of t you will multiply it with root 2 by t cos 2 pi FCT. You should remember this S of t is either plus or minus root 2 EB by t cos 2 pi FCT, right? This is what is our S of t. So you are multiplying it with actually what? Root 2 by t cos 2 pi FCT, right? So if you multiply that, what you will get? You will get, right? So if it is plus root 2 EB cos 2 pi FCT, you will get say root EB times 2 by t cos square something you will get, right? Cos square 2 pi FCT you will get 2 pi FCT. This is what you will get, right? Root EB times or plus or minus root EB times 2 by t cos square 2 pi FCT is what you will get, right? So, and in last class itself I told this cos square 2 pi FCT, it is nothing but what? 1 plus cos 4 pi FCT, right? Cos square 2 pi FCT is nothing but what? 1 plus cos 4 pi FCT. So this will be either plus or minus root EB times 1 plus cos 4 pi FCT, right? So now after this, what we have is in a coherent detection, we have an integrator, right? We have an integrator which integrates over a bit duration, right? We have an integrator, right, which integrates over a bit duration. This integrator is equivalent to actually what? A low pass filter, right? Integrator is equivalent to a low pass filter, right? So when you pass this thing through an integrator, so this is what we have here, right? This is what we have here, right? When you pass this thing through an integrator, right? So we have two terms. One is plus or minus root EB. So it is actually what? Plus or minus root EB. Then plus or minus root EB cos 4 pi FCT, right? So we have two terms now. This plus or minus root EB, right? When it is integrated, what we will get? Right, when, or you can assume it as a low pass filter or whatever, right? So this will be allowed, right? This will be allowed as such, right? Plus or minus root EB, right? It will be allowed as such. But this thing when integrated, what happens is this: we have assumed one complete cycle per bit duration, right? So we have assumed there is one complete cycle per bit. If frequency is FC, over a period of 0 to TB or over a period 0 to T, there is one complete cycle, that is FC. What if the frequency is 2 FC? Over this period, we will have two complete cycles, right? If it is 2 FC, over this period, we will have two complete cycles. So if you integrate it, what will happen? There is equal positive and negative areas, it will get cancelled, right? Or if you are seeing it as a low pass filter, what will happen? This is a DC term, right? This is a DC term. It's a constant, it's a DC term. So it will be allowed, but the high frequency content will be suppressed. You can see like that also, right? So what you will get here is actually what? Plus or minus root EB, right? Of course, weighted with T from 0 to T, right? So of course, right? Weighted with, but we are not bothering about that now, right? We are not bothering about that. So then whatever we are getting here, right? So we'll have a decision device, right? We'll have a decision device, right? Decision device which will take decision based on some threshold, right? So here if you see the constellation, right, we have 2 points, plus root EB or minus root EB, right? Plus root EB is the signal point corresponding to bit 1, and minus root EB is the signal point corresponding to bit 0, right? So I can take a decision, right, by placing a decision boundary at 0. If the received signal point is greater than 0, I can assume, right, if this received signal point lies towards the right of 0, I can assume a 1 was transmitted. If it lies towards the left of 0, I can assume a 0 was transmitted. This is what this decision device does. It will check, right, this, right, this whatever we have received here. If it is greater than 0, it will assume bit 1 was transmitted. If it is less than 0, it will assume a bit 0 was transmitted. So this is what we have to do, right? So, but in this case, this is the case of a coherent detection, right? This is the case of a coherent detection. But in case of non-coherent detection, we don't have a local oscillator producing a carrier, right? We don't have it. Instead, what we have is we have the S of t itself, right, with a delay of 1 bit duration acting as the reference, right, or acting as the other input to the coherent detector, right? So what you will do is the S of t for, right, 1 bit duration, right, S of t for 1 bit duration, right, will be multiplied with actually what S of t of previous bit duration, right? So this, in this case, right, we don't have to assume any initial value or anything. Why? Because we are receiving some continuous signal, and we have some mechanism for time synchronization, and it will tell us which is the bit boundary or a symbol boundary, right? So first bit will be allowed as such. We know that is a reference. First bit will be allowed as such. We know that is a reference bit, right? Second bit, what will happen is it will be whatever be the signal, right? Whatever be the S of t for the second bit duration, it will be multiplied with actually what the previous symbol duration. Then it will be integrated. Then a decision is taken. So what we have to do is you have to multiply signal, right, S of t of present or current symbol duration with a signal of previous symbol duration. Then we have to integrate, right? So this is what is DPSK demodulation is, and the whatever value we have got after this integration, if it is greater than 0, we'll assume a 1 was transmitted. If it is less than 0, we'll assume a 0 was transmitted. So this is what we are going to do now, right? So once again, I'll repeat. First step is actually what this, we have to multiply the signal with the previous symbol, right? A current symbol with previous symbol, right? It will be signals only, right? Call it's right. We have to multiply it, right? Then after that, we have to perform this integration. This is the second step. So to perform this integration, we'll be using trapezoidal integration. So for that, we have an inbuilt Matlab command, trapz. It's actually what trapezoidal integration, right? Then after that integration, we have to take a decision, right? If it is greater than 0 or less than 0. If greater than 0, we'll assume it was a 1. If it is less than 0, we'll assume it was a 0. Then we have to simply append the decision taken during each bit duration to get the demodulated signal, right? That's what we are going to do. So now in this case, any doubt is there, please feel free to ask. Any doubt in this case? Okay, I think most of you are busy doing your project, right? Simply logged in and doing your project. B section, any doubt? Yeah, okay, fine. So now we'll move on to the simulation part, right? Again, I'll just zoom it out a bit, right? I don't think, right? Slightly. Now, is this visible? With the zoom level, is it visible? I would be happy if someone can unmute and tell.
Yes, sir, visible.
Yeah, okay, fine. Thank you. Right. So we have PSK modulated it. Next, what we should do is we should demodulate it, right? So we are assuming a noise-free channel, right? So we have modulated and transmitted. So the we have named the modulated signal as modulated, right? So now we are assuming a noise-free channel. If you want, you can introduce a noise, right? You can introduce additive white Gaussian noise and add to it, and then you can try the same thing, same code. Only the modulated signal, you add some noise. That's it. Then after that, the received signal will be modulated plus noise you can, right? And remaining everything will be the same, right? So we are assuming the received modulated signal as such is received, right? Then we have to demodulate, right? We have to demodulate and get the data. So as usual, I have assumed the demodulated information to be a null matrix, a null vector, or a null array, right? And first, what I should do is I should multiply the present symbol with the previous one, right? I should multiply the present symbol with this previous one. So just remember, initially the raw data sequence had only 10 bits. After differential encoding, we have actually what 11 bits, but after demodulation we should get back only 10 bits, right? So for that, what we'll do is we are not assuming any previous bit or anything. First symbol we let it receive, right? Then we'll store it somewhere. Then second symbol, what we'll multiply with the first symbol, right? Then we'll take a decision. Then third symbol we'll multiply with the second symbol and we'll take a decision. That's what we are going to do, so that at the end we will get only 10 bits, right? So for this, initially what I should do, we should multiply a symbol with previous one, right? So for that, right, I have written it, say like this, right? Maybe we'll just see the logic behind this, right? So only time frame you have to consider, right? I'm not drawing the signal, right? So this is, say this is the first symbol, this is the second symbol, this is third symbol. Suppose there are 100 samples during each bit, right? During each bit there are 100 samples, right? During each bit there are 100 samples, sample 1 to 100, right? Sample 1 to 100. So first bit duration is samples 1 to 100, second bit duration is sample 101 to 200, right? I'll just write here, first bit duration is 1 to 100, samples 1 to 100, right? And second bit duration is sample 101 to 200. Third bit duration is samples 201 to 300, right? And in general, nth bit duration will be, in general, what will be nth bit duration? Right. If this 100, this 100 is nothing but what? I have defined t as actually what? Time vector for 1 bit duration, right? This length of t, is nothing but what it is? 100, right? So in one symbol duration, there will be 100 samples, right? So for, right, n is equal to 1, first bit duration, it is, if I write, please correct me if I am wrong, right? If I write the samples corresponding to nth bit duration, can I write like this? N minus, oh, okay, sorry, n minus 1 into length of t plus 1 to, right, n minus 1 into length of t plus 1 to n into length of t, right? So is this correct, right? So what I should do is, I have a signal s of t, or I have a signal modulated, or I have a signal received. That is nothing but what? Samples for entire bit duration, right? Samples for entire bit duration, right? Not entire bit, entire signal duration. So there will be 10 or 11, say 11 symbols will be there, or 11 symbols will be there in the received signal, right? So if this is t and this is 2t, so like that it will span up till 11t. So we have to consider actually what? Signal of duration, this 0 to t or 1 to t, and multiply it with signal of duration t to 2t, right? For that, I'm writing, right? So if first symbol, the samples are from, corresponding samples are from 1 to 100. Second is 101 to 200. So in general, nth samples of nth signal, nth symbol can be written as n minus 1 into length of t plus 1. So if you assume n is equal to 1, let n is equal to 1. Let n is equal to 1. So if you substitute n equal to 1 here, so 1 minus 1 is 0. 0 into length of t will be 0. 0 plus 1 is 1. So 1, 2. Then if you assume it 1 and length of t to be equal to 100, so it is 1 to 100, right? So for n is equal to 1, it is actually what? First sample to 100th sample. For n is equal to 2, you try. N is equal to 2. It is actually what? 2 minus 1 is 1. Length of t is 100 plus 1 to 2 into 100. So it is 101 to 200. So it is correct, right? So if I want to get signal of one particular symbol, right? So I should consider the n minus 1 times length of t plus 1 to n times length of t. That those symbols are what I have to consider. So maybe you can think through it, right? So I'll just show it here. So that's what I've done here, right? So Z in is actually what? Received of. So we are inside a for loop. We are iterating 1 to length of coded minus 1. Why? Because we have one additional bit, right? So we are not assuming any what previous symbol and all, right? So we have to iterate it from 1 to length of coded minus 1, right? Differential encoded minus 1. Then Zn is actually what? Received of. This is what I've told just now. Instead of n, I've used I here. I minus 1 times length of t plus 1. So this will be the first sample corresponding to that particular symbol to I into length of t. Last sample corresponding to that particular symbol, right? So this is the say nth symbol, right? This is this entire thing what I'm going to show here. This is actually what? Nth symbol received as a signal of that this sample to this sample, right? That is nth symbol, right? Or ith symbol, right? Into I plus 1th symbol, right? So when you're multiplying, you should use dot star. Why? Because these are arrays. We should perform element by element multiplication. So received of I times length of t plus 1 times I plus 1 times length of t, right? So this is multiplying ith symbol with I plus 1th symbol, right? So I should do it till length of coded minus 1, right? So ith symbol multiplied with I plus 1. So then what I should do is I should integrate it. For integrating, so the integrated result I am storing it in a variable set in underscore integrate. You can give any variable name which makes you sense, right? I'm using this trapezoidal integration. Traps t is the time base, right? T is the time base and Z in time base for 1 bit duration, right? We are doing it actually what? Bit by bit or symbol by symbol, right? So this t should be time base for 1 symbol duration and Z in is the 2 symbols multiplied, the resultant of multiplication of 2 symbols. So we are integrating it. So we'll the result will be there in Z in integral. Then this is our decision, right? If Z in integral it is greater than 0, we can take a decision as 1, and if it is less than 0, we can take it to be equal to 0. Then this term has to be appended to this received data. So bit by bit we are encoding, right? Bit by bit we are encoding and we are appending it to this received data, right? Maybe we'll run this. And then after that we are simply displaying it, right? After that we are simply displaying it. So we are getting back the original information 0 1 0 1 1 1 0 0 1 1, right? So we are getting this back. So this is DPSK, sorry, modulation and demodulation. Now I'll just, yeah. So this is the entire code, and there is one small mistake or confusion where you may get is initially we are defining only time vector for 1 bit duration, right? Then we are generating modulated signal bit by bit, then we are concatenating it, or we are appending it one after the other to get the final modulated signal. Right. Then after that, what we have is to plot the complete modulated signal, we have generated, I didn't mention it though, right? Generated a new time base to plot the modulated signal. So there we have actually what 11 bit durations, right? In 1 bit duration, we have capital T seconds. So we are assuming a time base from T by 99 to T times length of coded. Length of coded was 11. That's what we are plotting here, right? And similarly, for this integration, right, element by element multiplication and integration we are doing for 1 bit duration. So inside this trapezoid, right, the time base we should give that of a single bit duration, right? And this is Zn. So you can do it in many different ways. Maybe there can be what simpler or easier methods. You can use that. But finally, we should be able to implement the mathematical model. That's it. So this is all about differential phase shift keying. Right. So I'll share this code. Right. And now if you have any doubt, please feel free to ask. Did anyone understand this? What has been done? I think most of you are busy with your project work, right? So that's why most of you may not have even paid attention. But this time, right? What you should do is this observation, right? From now on, for you, for me to, right, have a grip on what's happening, and just to track, you are like doing it in time, right? Every week, I request you to submit this observation, right? So in that e-observation part, right, you have already shared for cycle 1, right? Cycle 1 you have already shared. So similarly, for cycle 2 alone, I don't want you to include the cycle 1, cycle 2, cycle 3, everything together, right? For cycle 2 alone, right, I'll just upload an e-observation. There you should, right, simulate and like include the code, and the diagram should be pasted, and you should write the inference, right? So maybe you can try and change so many things here, right? You can try and introduce noise, or you can try for different say values of energy per bit, right? Instead of considering a carrier frequency which has a complete number of cycles, if you consider any other carrier frequencies which has partial cycles within a bit duration, will it will definitely going to create some problem, right? It will definitely create a problem. So you can observe all those things, right? So those are some like additional tasks which you can do, right? So maybe today, for the time being, right, if you have any doubt, please feel free to ask. So at least you can type it in, whether you understood or not, whether you have any doubt or not. Right, it should not be A section, any doubt or no doubt? Please type it in chat window. And even B section, right? So today's attendance is going to be based on that, right? Your response. Please type in, right? Yeah, all of you should type in, like your attendance is going to be, right, taken from this chat transcript. And even B section, I request you to type in. No one has any doubt, right? I can't believe that. Right, maybe once you try with this, you may get some doubt. If any doubt is there, feel free to ask, right? And I repeat, before next lab, right? So anyhow, as you have a project evaluation this week, I'm not asking you to complete the observation, right? But after the project evaluation, right, before next weekend you all should have completed the observation, right? You all should have completed the observation. Otherwise, if you keep it pending, it will pile up, and at the end, it is going to be a problem for you people only, right? So maybe if I may ask CR, when can I keep the deadline for this observation, DPSK observation, A and B section CRs, or should I not keep any deadline? It's up to you, right? Oh, Catherine asking, will college reopen on 17th? Let's wait, right? Let's hope it opens. If it opens, actually, maybe we can straight away jump in and start doing our hardware experiments if you want, right? Okay, so maybe about this deadline we'll discuss later. Maybe CRs can discuss with your friends, and please message me, right? Would that be fine? Ligina is telling no deadline. So no deadline means it's equivalently no assignment, right? I don't mind, right? Right. But to drive you people, like there should be some deadlines, right? Without any deadline, nothing will happen, right? It's not why Pradeep Shetty is trying to join now, right? Maybe I should deny his entry, right? Not now. Yeah. So that's it. No doubt, right? No deadline, right? No, nothing. Yeah. So we'll end the session today. All of you, please do try. I'll post the code in Canvas along with the recording, right? So please.